Welcome students to MJC Learning. This is third lecture of current electricity. In previous lecture we talked about Kirchhoff first law, which was the amount of current entering the junction will be exactly same to the amount of current leaving the junction. Now we will be talking about Kirchhoff second law or Kirchhoff voltage law, and it also has another name, Kirchhoff loop law. So, Kirchhoff voltage law. In a closed loop, we have already talked about closed loop. Closed loop means the point at which the circuit starts, it will end at that point only, like A, B, C, D, A. In a closed loop, the algebraic sum of the potential difference and the EMF is zero. Here, potential difference means what? There will be different component on your circuit, like capacitor, like resistor, different component, inductor. So potential difference about that resistor, about that inductor, about that capacitor, all adding them and plus the EMF of the battery will be equal to 0. This also obeys conservation of energy. So it is simply written as summation of IR plus summation of EMF is equal to 0. Now what is this? This IR is actually is potential difference, that is V is equal to IR, Ohm's law. So now we will be talking about signs and convention used in this Kirchhoff voltage law. So conventional current, you all know conventional current flows from positive to negative. So if direction of current flow is same as the direction of tracing, then potential difference across the resistor is taken negative. First of all, what is this tracing? Tracing of a circuit is known as if you start from any point on a circuit and move from that point, then it will be called tracing of the circuit. Okay, so if the direction of your tracing, or you have also seen, if you have also moved to different places, like if you have walked on a certain circular way, then you will be called, you are tracing a circle. So here we will be tracing the circuit, means we will be moving from one point of the circuit to the another point. So direction of tracing and direction of current is same. If direction of tracing and direction of current is same, then we will be considering potential difference across the resistor is negative. Okay, so look at the diagram here. This is our circuit diagram. Here battery is there, resistors, 3 resistors are there, R1, R2, R3. This blue arrow shows the conventional current flow, that is from positive to negative, and the black line shows direction of your tracing, means from where you are going to start tracing. So I am going to start tracing from battery. So from battery I am moving in upward direction. Wait, let me show you. So from battery I am moving in this direction here. So direction of tracing and current is same. So potential difference about R1 is V1 by Ohm's law. By Ohm's law, V is equal to IR. So about this resistor, we will be having potential difference of V is equal to minus IR 1. And then again we are moving towards R2. So we will be having V2 here, which will be again minus I R2. Then moving to R3, which will be again minus I R3. So what I want to say is that blue line shows the flow of conventional current and black line shows the direction of tracing. If both are same, if both are in same direction, then potential difference about any resistor will be negative. I have written is potential difference across R1 will be negative, potential difference across R2 will be negative, and potential difference across R3 will be negative. Okay, I hope V is equal to IR is clear. Now next is, if the direction of tracing is opposite to the direction of current. Now if you can see the black line, it is moving in the opposite direction of tracing. So I will be starting from now here. Sorry, I will be starting from here in this direction. I will be moving in this direction from here to here. So first I will be considering R3. So it is in opposite direction to the direction of current. So potential difference about R3, R2 and R1 will be considered as positive. Again I am repeating, if the direction of tracing is same as the direction of current flow or conventional current flow, actually conventional current flow, so potential difference about resistor will be considered negative. If both are opposite, if we are tracing the circuit in opposite to the direction of conventional current flow, then potential difference about the resistor will be positive. I have written it here, potential difference across R1, R2 and R3 will be positive. So till now we talked about all the components of the circuit, not the battery. Now we will be talking about EMF. So we have to also consider about sign of EMF. So for considering the sign of EMF, consider positive. EMF is considered positive if it's going from negative terminal to positive. That is, if it is going from, this is your negative terminal, this is your negative, this is your positive. So if it is going in this direction, then it will be considered as positive. If the direction of tracing is in this direction, negative to positive, then it will be considered as positive. And if its direction of tracing is in opposite direction, so it will be considered as negative. So you can also consider that last terminal of your battery will decide the sign of your battery or EMF. So if last terminal is positive, then EMF will be positive. Last terminal is negative, then EMF will be negative. But why we are studying this science and science about potential difference and EMF? So in our first, this voltage, Kirchhoff voltage law, I have already shown you here that summation of all the potential difference about the resistors, we are going to only talk about resistor in current electricity, plus all the EMF, summation of all the EMF is equal to 0. And as in Kirchhoff law, we have talked about the current coming towards the junction will be treated as positive and moving away from the junction will be treated as negative. So there was also sign and symbol, and here is also some signs and symbol, so that our circuit analysis become much more easier. So our next is in circuit. So you can see direction of tracing is same as the direction of here current flow. So here are some batteries, or you can say potential difference of that, there are some EMFs V1, V2, V3 and V4. I have specifically mentioned V1, V2, V3, V4. For simplicity, we are taking the flow of current and the direction of tracing in the same direction. So look at the first terminal, how it will be taken. If you are moving in this direction, if you are moving in from this direction, okay. So what is the last terminal of your battery? That is positive. So V1 is positive. Here, what will be your last terminal? Negative. So V2 is negative. Here, V3 is negative. Here, V4 last terminal negative. Therefore, V4 is negative. And summation of all those EMF will be equal to 0. Now, putting both those signs and convention in the question, now in the question itself. So in a certain example, so here EMF is also there and resistors are also there. Both are connected, and now we are going to decide what will be the equation of KVL or Kirchhoff voltage law. So first diagram and second diagram. First I have considered that both direction are same, and in second example I have shown you tracing direction is opposite to the direction of current flow. So first, for EMF, because only one EMF is there, direction of tracing is from negative to positive. So value of E will be positive. Potential difference will be, they both are in same direction, therefore R1, R2, R3 will be negative. So here summation applying KVL, Kirchhoff voltage law, that is summation of EMF plus summation of voltage differences about the resistance, that is IR, according to our Ohm's law, will be equal to 0. So E, that is positive, I have already shown you how it should be positive, and IR, that is summation of all the IRs, which are negative, minus IR minus IR2 minus IR3 is equal to 0. Now you also have to see that the current here is not changing because they all are in series. Okay, so in series we all know that the current doesn't change. So here current is same. If some resistance will be in parallel, then current will definitely change because there will be the formation of nodes or junction where your current will divide in 2 or 3 parts depending upon the branches. Now in second example here I have shown you that the tracing direction, that is black arrow, is in opposite direction. Again for the EMF, it is going from positive to negative, so EMF will be negative. Potential difference will be, they both are opposite, therefore potential difference will be positive. So summation of E plus summation of IR will be equal to 0, minus E plus IR1 plus IR2 plus IR3 is equal to 0. E is equal to IR1 plus IR2 plus IR3. Both equations are same, so you don't have to worry about which method to be followed, but I will prefer this method that both direction is same because it is much more simpler way. You don't have to think about a lot, but you have to remember at least one of them, so to solve different questions. Okay, now we will be talking about something. There is no ideal EMF. I guess you have already studied in 11th standard. There are no ideal batteries. They also have some internal resistance because it is made up of some material. Its internal material also will be having some resistance. So its internal resistance will be mostly shown by small r. So again same, if you can see here, I have shown you there is a battery. There is a battery here, this is the battery and this is its internal resistance, and I have represented it with small r. So if direction of current flow is in this direction, so direction of current flow is in this direction, then this equation will be used, E minus IR. That means actual potential difference or actual EMF of the battery is been reduced by your internal resistor. And if direction of flow is in opposite direction, that is from positive to negative, then we will be taking only negative sign in front of this. You can see it will become minus ER plus IR. In both the case, internal resistance will definitely reduce the EMF of the battery. I hope this point is also clear. Now this is a very big example. Now we are going to consider this example. This is a big example. So this is the circuit with many EMFs in it, E1, E2, E3. Now look at this R1, small r1, R2 and R3. These are internal resistance of your EMF. Okay, so I am considering a closed loop. Considered here is F, A, B, C, D, E, F. Now look very closely. I have started with the letter F and ended with the same letter F. This is how we represent closed loop. I hope this is clear. Now direction of current flow is again represented by a black arrow. Okay, this all you have to do by yourself. So here I am starting with the letter F here. So my starting point is this F. So I am going in this direction. So here last terminal of EMF E1 is positive. So here which equation will be used? Is this equation, E minus IR. So E minus I1 R1, because I1 current is flowing. Now again direction of current flow is written shown by red arrow. So it is moving in this direction. Tracing is also in the same direction. Therefore potential difference about R1 will be minus I1 R1. What will be R2? Minus I1 R2. Now what is our loop? Our loop is this one, this bigger one. Okay, I am not considering this part, not this one, this part. I am not considering this part. I am only considering this part. So from R2 I1 R2 is over. So now this B point is a node point or junction point. Here current will current will divide in two parts. This is I2 and I3. So I3 will move in R4. Therefore, we will get again same direction, same tracing direction is same and current direction is same. So I3 R4 minus I3 R4. Now this E1 E3. So again direction of current is from negative to positive, negative terminal to positive terminal. Therefore, EMF will be E3 minus I3 R3. This I have double lined with yellow color here. Now next is R5. Therefore, R3 R5 same direction, so it will be again negative. Now last is R6. So again this direction is same, so therefore it will be negative, so equal to 0. I hope this is clear. Now closed loop FABEF. What is this closed loop? FABEF. So this small loop I am considering. I am just considering it. I am not solving anything right now. Okay. So I am just considering it for understanding better signs and symbols. So here I am starting with F. Again same E1 minus I1 R1 small r1, then minus I1 R1 capital R1. Here minus I1 R2. Now from at point B, current will get divided in two parts. I am not considering this B to C1, so directly B to E. Look at our closed loop here. So it will be minus I2 R3. Now this EMF is going from positive to negative. If it is going from positive to negative, so what should be then? Positive here. Here also current is moving from positive to negative. So minus E minus IR. So we have to consider this equation. So I have written it this equation minus E2 minus I2 R2. Okay, small r2. Then directly E2F, that is R6 I4. Okay, so in this way I have closed the loop and solved. We will get some equations in our circuit, and in our next lecture we will be looking at some of the questions. I hope the lecture is clear. I hope the Kirchhoff voltage law is clear. Kirchhoff voltage law is nothing but summation of all the potential difference about the component plus all the EMF, summation of all the EMFs in a circuit or in a closed loop will be equal to 0. If you remember Kirchhoff voltage law, you can remember it by Kirchhoff voltage law or Kirchhoff closed loop law or Kirchhoff loop law. Okay, thank you.